All right, good morning, everyone. Let's get started. So some people, hopefully not too many in the room, but people that will watch the recording, will want to know where you are on the wait list. If you email me, I'll get back to you, and I'll just tell you, I'm not going to give out much explanation. I'll just say what your number is in the wait list. Talking or exchanging an email with Lori Fisher, about 25 out of the 50 people that are supposed to be added have been added. She said that EC students need to fill out a form, so that delays things. And some people that were to be added have decided not to take the course after all, so more than the initial list of 50 will, or some people that were not on the initial list of 50 will get in. But I can't tell you, I can't say what the number will get to. I can only tell you what number you were on the original list. So if you want to know that, you can email me. Any questions? So one more thing that's a repeat of the announcement last week. Currently, we do have, there's 2 free seats, but we're pretty close to over full. So if if there end up being more people than there are seats, that means that some people who are not registered for the main section are here. And while I generally would encourage attendance, if you're not in the main section, because the section is full and because so many people are coming to class, which is good, it's over full. And fire codes don't let people, we can't let people like sit in the aisles. So if we end up, there's still 1 seat here, and another seat back there. If we end up with not enough seats, then I'm going to need to ask some people who are not registered for the main section to go. There's a seat over here. Okay, so let me start by reviewing image filtering. Just briefly. So the idea, so last class we talked about filtering in the spatial domain. Sorry, I'm just checking seats. All right, so we're over full. So I announced last class that I can't have people that aren't in the main section here unless there's space. So if you're not in the main section, I just need a few people to go and watch the video. I'll have to start doing a roll call. So we've got more people than seats. Actually, I can have my TAs for now. If you guys, I can bring over some chairs for you if you could take the chairs. Because actually the TAs probably overfill it as well. All right, so there's a seat up here. Okay, thank you. Okay, so last time we talked about spatial filtering. So basically the idea is that you have some filter like the box filter there, and you slide it over the image, and at each position, there are a few seats here if you want to take one. At each position, you multiply the elements of the filter with the corresponding elements of the image, and take the sum, and then that's the response of your filter. And you store that response at the center of where the filter was. So for example, here, the response is 0. It's a bunch of zeros times 1/9. Take a step to the right. The total response is 10. It's 8 zeros times 1/9 plus 190 times 1/9. There are seats up here if you want one. Take another step. Now it's 20 and 30, blah, 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 and so on. So after applying this box filter to the whole image, we get a kind of smoother image. And you can also view this as a local averaging filter. There's lots of things that you can do with these filters. You can detect edges, for example. So here the gray is, one important thing to note that I didn't say before is you can display images that are not in the RGB range if they're like single channel images. So here, this image is rescaled so that 0 is gray, and high numbers are white, and low numbers are dark. So the gradients, the places where you have an edge are either dark or white. That's just an important thing to note because sometimes there's confusion about like how do you view the response of an edge filter when it creates negative numbers. In MATLAB, if you use Hoiem show, then you'll get a really dark image. You won't be able to see anything at all because Hoiem show will assume that you're in the normal RGB range, which for floats is 0 to 1. So you want to use image SC, or I think if you give an extra parameter to Hoiem show, then it will rescale the image for you, or you can rescale it yourself by math.
So when you have an RGB image for a photo with 3 channels?
Yes, so if you have a RGB image, then you can use, if you're using Hoiem filter, the syntax is still just that you do Hoiem filter im and the filter. And if you have 3 channels or 1 channel, it will apply it to whatever channels you have. And then the output will be, if you have a 3-channel input, then the output will also be 3 channels. There's a seat, there's still one empty seat here. So today we're going to talk about filtering again, but rather than talking about it in the spatial domain, we're going to talk about it in the frequency domain, so using FFTs. And this gives us a different view of filtering and what it does, and it gives us a better understanding of some applications and the behaviors of filters. So for example, there's a bunch of questions that are kind of hard to understand if we don't understand the frequency domain, if we're only thinking in the spatial domain. So like this Gaussian and a box filter both look kind of similar. They both create a response that's based on the weighted average of a local neighborhood. And the box filter is a direct mean filter, averaging filter. So it seems like it should produce a really nice smooth image. But if you compare the two, this image has a lot of like little edges that are created where the Gaussian is truly smooth. And so that's something that we can understand once we look at the frequency responses of these filters. Another example is hybrid images. So this is a kind of neat little paper by Ode Oliva and Antonio Torralba and Shins. Ode Oliva is visiting campus, by the way, in a couple weeks. So the idea here is that you can create a single image that's a blend of 2 other images. And when you look at the blended image from close up, you see one thing, and when you look at it from far away, you see another thing. So for some of you, if you're towards the front, when you look at this, you'll probably see the leopard more. And then when you look at this, you'll probably see the elephant more. And so your interpretation depends on your distance. Again, that's something that's easier to explain in the frequency domain than the spatial domain. So like, why do we get these different distance-dependent interpretations of hybrid images? So this is me and my cat. So this, you probably see the cat, and this, you probably see my face more. So we need to understand frequency to understand how it's possible to create an image where you interpret it differently depending on your distance. And then finally, why does a lower resolution image still make sense to us? So we take it for granted that you can just shrink an image and it still looks like the same image but smaller. But if you were to, for example, shrink an audio file just by rescaling it, it would actually change your interpretation of the audio file quite dramatically, get like really high-pitched. So why is it that we can shrink the image and still have it feel like it's maintaining most of the content? And what is it that we actually lose when we do shrink the image? So to answer all these questions, we have to learn to think in terms of frequency. If you take a signals class or maybe an image processing class, you might have a more mathematical approach to working in the frequency domain. I'm not really interested in doing that, but mainly I want you to have a good intuition for thinking about images and filtering in the frequency domain. So we're not going to do like integrals of imaginary numbers with real signals or anything like that to mathematically compute the responses, we can just use FFT2, the MATLAB function. But we're going to look at the responses in the frequency domain and try to develop an understanding of a more intuitive conceptual understanding of what's happening. So, the FFT Fourier transform goes back to Fourier, who had this idea in 1807. And the idea was that you can represent any univariate function as a weighted sum of sines and cosines of different frequencies. So it's not an idea that would occur to most people. Most people probably wouldn't think of trying to create functions out of sines and cosines. And it's a kind of, people didn't pay it much attention at first. So he actually submitted it to a mathematical competition, and it didn't win. The judges were Laplace, Lagrange, and Legendre, who are all very prominent mathematicians. Some of the most famous mathematicians ever. I really like that. This is like the only photo that I can find of Legendre. I mean, the only depiction. So Lagrange says the manner in which the author arrives at these equations is not exempt of difficulties, and his analysis to integrate them still leaves something to be desired on the score of generality and even rigor. So if you ever get a bad review for a conference paper, you can console yourself with that, that Fourier got his FFT paper rejected by Lagrange. So it wasn't even translated into English for 70 years. So even when, at the time that he did it, there wasn't really an application. It was just like, hey guys, look, I can make a signal out of sines and cosines. That's pretty cool. So it's true, though. His idea was true, except there's some exceptions on the types of functions. But for most real continuous signals with an infinite domain, you can reproduce them by adding up sines and cosines. So here's an example. It's a little bit easier. I'm going to start in 1D first because it's a little bit easier to think about that before we go to 2D. So for example, if I want to produce this square wave, then I can produce it out of an infinite series of sine functions. So I start with a sine function that's kind of broader sine function with a frequency of the same width of the square wave, and then I double the frequency, or I increase the frequency by 1, and then I increase the frequency, and then I keep on doing that and adding each successive signal, which has a smaller amplitude but a higher frequency, and then after I add enough of these, I'll get the square wave. So we can represent these sinusoidal functions, instead of just representing them as in the spatial domain, we can represent them in terms of a power and a frequency. So for example, this sinusoid here has an amplitude of 1, and it has a frequency of f. This faster sine wave here has a frequency of 1/3, an amplitude of 1/3, and a frequency of 3f. So when I add them together, I get this signal in the spatial domain and this signal in the frequency domain, where I see that I've got an impulse at a frequency of f and a 3f that corresponds to the amplitude of those components. So as I keep on adding these additional sinusoids, I get closer and closer to the square wave that I'm trying to create. And then when I look at it in the frequency domain, you can see that I've got this function which is I'm adding together a set of sinusoids at increasing frequency and decreasing amplitudes. So the amplitudes are some a over k, where k is, and the frequencies are proportional to k. So now we see frequencies in 1D a lot. So for example, with music. So I could interpret this as, in fact, music makes a lot more sense to us typically in the frequency domain than the spatial domain. So here's a waveform. This is the amplitude as a function of time, which is kind of the analog to an intensity image. But in the spatial domain or time domain, it doesn't really make much sense to us. Like you can sort of see that it got louder here and then quieter, so loud, quiet, but you could never interpret this and be like, oh yeah, that's Twinkle, Twinkle, Little Star. I mean, not that you can necessarily do that by looking at this frequency domain either, but at least you can see like, oh, there's a lot of low pitches here and not too many high pitches. This is more of like this is actually, might be like a voice signal for somebody with about an average or deeper than average voice. So you get more information from the frequency domain, or at least it's easier to interpret. But any signal can be decomposed into the frequency domain, not just ones that we're used to seeing that way. So for example, like here's a picture of my cat, Tesla, when he was a kitten. And so here's the frequency image. These contain the same information. In this case, we're used to seeing it that way. We're not used to seeing it that way, but they contain the same, well, actually, they contain almost the same information. Well, part of the same information. Technically, I'm not showing you the phase image, which is also required. I'm just showing you, so basically, I'm showing you the powers of the frequencies here. There's also a corresponding phase image that that tells you how the 2D frequencies line up. So let's look at Fourier analysis and images, and let's start with sinusoids to keep it simple. So now we've got some 2D sinusoids. So this intensity image here has a low frequency, and it's varying in the x direction, right? As you move across from left to right, then you get the changes. And so the Fourier image has this amplitude of 1 probably, that's with like little dots. So the way that these these images are arranged, the center is DC, meaning 0 frequency. The edges are high frequency. A high horizontal frequency goes along the horizontal direction. A high diagonal direction frequency goes along the diagonal direction. A high vertical frequency goes along the vertical direction. And the Fourier amplitude image is, or the Fourier images are symmetric about the origin. There's an amplitude image and there's a phase image. And I'm just showing you the amplitude image because the phase image usually is difficult, very difficult to interpret, as I'll show you later. So here we've got a sinusoid that's faster and going in the horizontal direction still. So it's got a couple of dots that are wider apart. So that means that they have higher frequency than, that you've got power in the higher frequencies than in this one, still in the horizontal direction. And then we've got one in the diagonal direction, and so you can see that the frequencies are in the diagonal direction. Now you can add together these signals. You can add them together in the spatial domain. You can add them together in the frequency domain. And the addition is just an element-wise addition. So here you see them combined, and now you get a slightly more complex image, and then that corresponds to the slightly more complex frequency, the amplitude image. So for a natural image, you're going to get an actually quite complex FFT amplitude image, but there's actually a lot in common among different images, and I'll show you several examples. So as I was mentioning, again, it's worth repeating, if you have a strong vertical frequency, which actually means a horizontal edge, because if you've got an edge going that way, it means you have a lot of change as you go up to down, then it's going to show up here. If you have a strong horizontal frequency, it'll show up over here. Low frequencies are over here. Notice how most of the power is in the low frequencies. This is log scale. So all of this stuff is actually not a lot of power. All the power is very concentrated in the low frequencies. Images are smooth. And so like this diagonal frequency probably corresponds to like the edges of the opening here, as well as like this edge and the edges of the floor. You can also note this is actually pretty weird to see like this pattern of like these wandering frequency amplitudes over here. That's probably because of the camouflage pattern. So, so the Fourier transform stores the magnitude and the phase at each frequency. The magnitude encodes how much of a signal there is at a particular frequency, and the phase indirectly encodes the spatial information. So the phase of a sinusoid tells you how the sinusoid is shifted. So here's just a little math. This is actually sometimes useful. So if you want to take, if you do a FFT, if you call FFT2, you should get back a signal that's the same size of the image that has a real and imaginary component, and it should be symmetric about the origin if the image that you gave it was a real image, meaning real as in a real number. So here's the real part of the signal and the imaginary part of the signal. If you want to compute the amplitude, then you just take the length of those two numbers. If you want to compute the phase, you just take the arctangent of those two numbers. And sometimes you also see Fourier transforms denoted in this condensed Euler's formula notation. So there are formulas that can be used to compute the Fourier transform, but we're not going to do that. It would be, ridiculous to try to do it by hand. So we'll use what's called the fast Fourier transform, which is an efficient algorithm for computing FFTs. The fast Fourier transform is on the order of n log n. So if the size of the image is a factor of 2, so if it's a power of 2. So if your image is like 1024 by 1024, then the Fourier transform is on the order of n log n. And that's important to remember because sometimes, as I'll show or as I'll explain in a little bit more later, doing the filtering with the Fourier transform can be faster than doing it in the spatial domain if you've got a really large filter. So but just in case you're curious, this is how you would compute a Fourier transform in the continuous domain. This is how you compute it in the discrete domain. Images are discrete, so we're always working in the discrete domain. So this is a really important theorem, and it's basically why we care about, part of why we care about Fourier transforms in a vision class. The convolution theorem says that the Fourier transform of the convolution of two functions is the product of their Fourier transforms. So that means that if I want to filter G with H, or if I want to convolve G with H, and here the distinction between convolution and filtering, which is just convolution is doing filtering with a rotated filter, can be sometimes important to keep in mind. But if I want to convolve G with H, then one way I can do it is compute the Fourier transform of G, compute the Fourier transform of H, and then element-wise multiply them together. And then if I want to get back the filtered image, then I can use the inverse Fourier transform, because the inverse Fourier transform, or the product of two Fourier transforms, is the convolution of the two inverse Fourier transforms. So there's a nice, I can nicely use Fourier transforms to do filtering and then get back the filtered image. There's a nice relationship between convolution and in the spatial domain and multiplication in the frequency domain. So if I do Fourier G, Fourier H, element-wise multiply, and then inverse Fourier, then I get back the filtered image in the spatial domain. Now, if you imagine that G is the same size as H, if I were doing the filtering in the spatial domain, this would be on the order of n squared if there are n pixels. In the frequency domain, it's n log n, because I've got n log n for each Fourier transform, and then the dot product is just order n. And then an inverse Fourier transform is also n log n. So convolution in the spatial domain is equivalent to multiplication in the frequency domain. So here's some important properties of Fourier transforms. As you would expect, since convolutions are linear, Fourier transforms also have the linearity property, meaning that if you take the Fourier transform of ax plus by, then that's the same as a times the Fourier transform of x plus b times the Fourier transform of y. The Fourier transform of a real signal is symmetric about the origin. It has the same number of, it still has the same number of variables, I guess, as the original image, but they're stored in real and imaginary coordinates. And so it only takes up half the image to store those numbers. The energy of the signal is also the same as the energy of its Fourier transform. So doing the Fourier transform and inverse Fourier transform preserves the energy, meaning if you took the total square magnitude of all the pixels or of all the Fourier transform values, then the sum of those squared values would be the same in both cases. So in the spatial domain, we do filtering by sliding the window over the intensity image, taking the dot product, storing the response. In the frequency domain, you take the FFT of the intensity image, and I'll show you code a bit later. That gives you your Fourier image. Here just the magnitude is shown, the log magnitude. The reason that we show the log, or I show the log, is that this is just so much stronger than the rest of it that if I just showed the linear magnitude, all you'd see is like a dot in the center. So also I take the FFT of this filter, and note how it's got hypnotizing circles around like the horizontal, like slightly offset in the horizontal direction. That's because this is detecting horizontal edges, which means that I'm detecting changes in the vertical direction. So the power of this filter is in the horizontal direction. So this is where it's going to preserve the frequencies. It's preserving the frequencies that are powerful in the horizontal, or that it's preserving the high frequencies in the horizontal direction. So I multiply these together, and this is just an element-wise multiplication. And now I've killed that low frequency. So there's not much, the average intensity of the image will now be about 0. And I also have just like basically preserved like this part of the spectrum. And that results in this image once I take the inverse FFT. So I'm only preserving the like strong horizontal frequencies from the original image. Question? Yeah, that's a good question, and I'll show you, let me just show you the code, and then I'll show you the demo. So I'm going to show you a demo of a bunch of examples, and this is basically the code that can be used to do that. So I've got some image. Here I'm assuming a grayscale image. You would have to process RGB separately. I've got a size of an image, and I'm going to say what size I'm going to use for the FFT, which means that here I'm padding, when I call FFT2, I'm padding the image to go up to 1024. And then I'm also going to, when I compute the FFT of the filter, pad the filter so it's the same size. So you need to pad the filter so it's the same size as the image. And you want it to be a power of 2 because the fast FFT is more efficient if your size is a power of 2. So this is bigger than the image size. I've got my filter here. I create a Gaussian that's 101 by 101, so it's a pretty big smoothing filter with a standard deviation of 10. Did the Fourier of the image, did the Fourier of the filter. I just dot multiply, so that's element-wise multiplication of the image with the filter. And then I did the inverse FFT, IFFT2. And then finally, because I had padded the original image, I removed the padding here, and then display it. So when I display it, this is FFT shift, just shifts it so that the 0 frequency is in the center. In the original way it stores it, it's like kind of off in different quadrants. Absolute value, log, image SC rescales the values, and by default displays in the jet color map. So that's the code that I'll be using to do FFT filtering. And now, this code is also posted. And now it's going to make me like pull over every figure individually. So here's figure 2. All right, so here's one example of an FFT of another image. This is Monaco from Monaco. So here you can see that there's some power in vertical edges and some in horizontal edges and some in this diagonal direction. Maybe that's due to some of these edges along the window frame here and here. This has the classic shape for a man-made scene. Yep, one second. The classic shape for a man-made scene is that you have this kind of star pattern. Part of this star is actually because there's the image is padded with zeros, so you've got actually a sharp edge on these boundaries. But in any man-made scene, you've got a lot of horizontal and vertical edges, so you get this kind of star pattern where you've got a lot of strength in the zero frequency, but also some moderate strength in the horizontal and vertical edges. Is there a question?
First, if we rotate this image, we get a rotated version of the frequency domain as well.
Yeah. So if you, I'm not sure. I don't think it would. I haven't thought about it, but I don't think necessarily rotating the image would be the same exact image as rotating the frequency domain. But for example, if I turn it on its side, then anywhere where I have a strong horizontal frequency, I would now have a strong vertical frequency.
Right. I was saying that if I rotate it by 10 degrees to the right, the pattern should move because the edges have also moved.
Right. Yeah, that's.
Because the intensity along the axis seems to be really high, even for very high frequency.
Yeah, I think that.
Is it because of the image ending?
Yeah, I think that some of these super high frequencies are actually just because if I plotted zeros around this image, which is what it's always computing based on, then you'd have sharp edges where you go from these bright colors and moderate grays to zero. So if I padded and applied a smoothing filter to the padded image, then it would kill some of these frequencies that are really strong here. But because these are this frequency basically means that you went from white to black in 2 pixels. Or you had a big change in 2 pixels that wasn't a pattern that was elsewhere, that it wasn't part of a longer pattern in the image. So this would look similar, but maybe some of these very strong frequencies would be attenuated if I padded and then blurred before doing the FFT.
The vertical edge detecting filter that you applied had this symmetric pattern of 2 blocks.
Mm-hmm.
Wouldn't something which filters out everything on the x-axis be more desirable than something which focuses on some higher frequency and not the more higher one?
Yeah, so the question is why, I don't have a great answer to this, but the question is why not make some filter in the frequency domain, for example, and then apply that to the image. So if you could design a filter in the frequency domain that just tries to preserve this whole strip. I don't know if you want the zero values or not, but preserves whatever you want to do. And I would play around. It's easy enough to play around with. What will happen if you do that is you'll probably get ringing in the output image. You'll get some weird artifacts because you're filtering with an image. If you look at the inverse FFT of that image, it's going to look unnatural, and it will produce some usually undesirable effects in the input image. I don't have though a really pat answer for why for images because in other domains you might design a filter in the frequency domain and then use that. While images we kind of design it in the spatial domain and then look at it and then can think about it in terms of frequency. I'm not sure why exactly. So. It's probably there. Okay, so that was just one image. So here's another example. It's a waterfall. There's a lot of texture in all directions, natural image. And there you get a more rounded FFT because you've got lots of frequency in many different directions. So you've got this kind of more blobby, equally distributed pattern, still concentrated in the center. You still have this like these stripes here because of that, the edge of the image. And so what do you think this will look like? So where do you think like the main directions of high frequency will be? So if someone wants to answer, you can do it by gesturing. Just don't karate chop your neighbor. Yes?
I think there probably will be something like this line from the bottom right to the top left, because there's an edge from left to right.
Mm-hmm. Yeah, so it's saying that there's probably like some power in this direction, right? Right, because you see a lot of these rooftops here that are all slanted, for example, as well as the shadow edges here. Yeah, so that's the one that's maybe might be non-obvious. So there's also, if you go left to right, again, there's a lot of edges from all these vertical poles and bricks and stuff, the edges of the buildings and windows. And if you go from top to down, again, there's like some texture in the bricks and in other patterns that will create edges. So if we look at it, we indeed see a lot of power in this diagonal direction due to all the rooftops and all the edges that are oriented this way. And then we also see some power in the horizontal and vertical directions. So what about this image? Yes?
A lot of horizontal edges, somewhat down from left to right.
So what way, yeah, so there's a lot of horizontal edges. So what way will the power be? What direction will is the frequency? No, so there's a lot of horizontal edges, so the frequency is actually vertical. So you always have to think of it as where is it changing? It changes as you go from top to bottom. So, and that's what you see. There's a lot of power in this direction, not so much in this direction now. And, basically it's almost all the high frequency power is in this orientation. All right, so now I'm doing filtering, and I have to, again, drag some figures over. So here, this is the one that we saw before, I think. I've got 6 of these. I should probably change this code sometime to use subfigures so I don't have to drag them. Okay, a couple more. So don't hit the X. Yes, there's filter. All right, so the format of these examples is you've got the original image, the FFT of the original image, the filter, the FFT of the filter, just showing the log FFT magnitude. Oh, no, sorry. The FFT of the filter showing the log FFT magnitude. The filtered image, which is the dot product of this and this. I mean, not dot, sorry. Pointwise multiplication of this and this. Inverse FFT. And the log FFT of the filtered image. Let me just switch a couple of these orders because I think it makes more sense. So now, so this figure here is the log FFT magnitude that's produced by pointwise multiplying these two. And then doing the inverse FFT, I get the filtered image. Okay, we did that example before. Here's another one. So here's with the Gaussian. So here you can see that the Gaussian has a nice, the FFT of a Gaussian is also Gaussian, which is kind of nice. So you can see that it's preserving the low frequencies. And indeed, when I multiply it with the original 4AH signal, then I'm preserving just the low frequencies are preserved. And these, like you can see these visually, but they're actually really low because it's in log space. This, and then this is the filtered image, which is the blurred original image. Question?
Where's the extra location of the original pixels stored in FFT image?
It's not, so there's no like, it's not easy to extract, for example, the intensity of a particular pixel from an FFT. It's a completely different way of representing it. So it stores, you've got your phase image and your amplitude image, and the intensity at a particular pixel will be the result of combining many frequencies at different phases. So you lose, with the pure FFT, you lose all that easy access to where things happen in the image. So sometimes people use something called windowed FFTs, which is where you slide a window across the image and you compute the spectrum within each window. And then you get the spectrum, then you get the frequency, some information about the frequency that you can localize to a part of the image. Another nicer compromise actually is something called a wavelet transform. So for a wavelet transform, you decompose the image successively into higher and higher frequencies, and you can think of it roughly as frequencies in the horizontal, vertical, and diagonal direction. And for each of these responses, you get some map. For each filter, you get a filter response, which kind of gives you some sense of where and how much power is in each of these frequencies. I think we'll talk briefly about wavelets in another class. So sorry, just to repeat the question that I answered. The question was, where is the information stored about the location of a pixel? I think, right? Or like, where is the pixel information stored? So here's another example. This is called a Laplacian of Gaussian. It's actually an impulse minus the Gaussian. So this is our sharpening filter. And you can see that it's the exact opposite of a Gaussian. It's 1 minus the Gaussian response. So it's going to attenuate the low frequencies and preserve the high frequencies. And so that's what it does. It knocks out that 0. And so I've preserved the higher frequencies. And now the average response will be about 0, and the low frequencies are gone. Whoops. OK, so here's the box filter. Now you can see that this one does something kind of weird. The response of the box filter is not a nice response that just focuses on 0. And that's because of these sharp edges here, right? And the box filter is basically a 2D version of the sync filter, of a square wave filter. And so its Fourier response is a 2D version of the sync function. So just like the square wave had some patches, had like spots of high frequency at decreasing amplitude, the box filter also has these spots of higher frequencies at decreasing amplitudes. And so it preserves not only the low frequencies, but it preserves these isolated little spots of high frequency. And so that's why it's not the best smoother. OK, so back to PowerPoint. And I do have another short demo later. OK, so I already went through this, but you can look at it more on your own. So one question is, what do you think has more information, the phase or the magnitude of the image? I've shown you So far, I've just been showing you the log amplitude images, which are kind of nice to look at and intuitive. What do you think is what do you think really contains the signal of the image? How many people think that the amplitude has more information? Some, maybe 15%. How many people think that the phase has more information? Okay, about 50%, and about 30% are not venturing to guess. So one way that we can answer this question is to think about, or is to experiment with, what happens if you take the phase from one image and combine it with the magnitude of the other image? Will it look like one of the images? Will it look like the image that we took the phase from, or the image that we took the amplitude from, or neither? Will it make sense at all? So I can do that. No. Ooh, okay. So here's an example. If I'm going to combine the phase from one image with the amplitude of the other. I'm going to use y. So I have to do a bunch of dragging again. Oh, I probably closed the figures in the code. All right, so let me drag stuff over, and then I can explain what's going on. Okay, so here's the Monaco image again. And here is the waterfall image again. And this image in figure 3 is the result of combining the phase of the waterfall with the amplitude of Monaco. And this image in figure 4 is the result of combining the phase of Monaco with the amplitudes of the waterfall. So you can see that in order to, it's not that it's really solving something, but in order to maintain the amplitudes of Monaco, this image has to have a lot more stripes in it. It has to have a lot more edges, right? So it kind of like has a lot more of an edgy pattern, but the layout of everything still corresponds to the waterfall image. So it looks more to us like the waterfall image. And this one also, like the layout of things looks like Monaco, but it has a more splotchy pattern because it has to have roughly equal power in the frequencies in all directions. And so it's preserved those powers. But so you can see that the phase is actually what's containing most of the spatial layout information that is useful to us for interpretation. This is what a phase image looks like. You can't really look at it and say much from it. But note that something that looks like a random pattern usually has a lot of information. It's hard to compress. So let me just show you that code because it's pretty simple. Another drag. All right, so what am I doing in this code? And you can play with it on your own since the code is posted. So all I did here was I take two images as input. I compute the FFT of each one. For each one, I compute the magnitude with abs and the phase with angle. And then I show the images. And then I do, and then I combine the phase of M2 with the magnitude of M1 by recomposing my imaginary numbers here. So I do cosine of phase times the magnitude plus imaginary I times the magnitude times the sine of the phase. And then I do the same thing for the other pair, but swapped. And then I show the images. So the phase has all the spatial information in it, but not in a way that's very easy to interpret. Okay, so to summarize that part, so why does, or not summarize, but now we can answer this question easily. Why does the Gaussian give a nice smooth image while the square filter has these edgy artifacts? I suppose we're recapping. Right, so the answer is because there's more high frequency preserved in the box filter. Yeah, so the box filter, the Gaussian kills all the high frequencies. The box filter preserves some of the high frequencies. And those high frequencies show up as these kind of edgy patterns in the straw. So, all right, I'll just do a couple of these. So here's a problem of trying to match the Fourier magnitude image with the original intensity image. So let's do E. So which Fourier image do you think corresponds to E? You can just shout it out. 5? 4? Okay, there's more 4s. 4s are the popular vote. And yes, 4 is correct here. So there's a lot of edges. There's a lot more edges in the vertical direction in this case than horizontal, where 5 corresponds to what? C, right, because there I've got a lot of, like, it's kind of dark image, but there's a lot of horizontal and vertical edges which give us this star pattern. 1 corresponds to D, right? It's a Gaussian. 2 corresponds to B, right? Natural image, that nice round pattern. And then the remaining pair is 3 corresponds to the edge filter. All right, so there's another question that we can answer from what we've seen so far. Why does a lower resolution image still make sense to us? And what do we lose when we go to a lower resolution? So first, why does it make sense? Why is it that this image still feels like it contains most of the information? Am I? I'm not sure if I am, actually. I haven't ever thought about that. But that's, I guess I showed, so I showed before when we swapped the amplitude and the phase, it kind of looked more like the phase image. But I definitely wouldn't say that it preserved most of the information. It looked pretty messed up. Where these are like, the same thing basically, but one is just smaller. So that's not quite the right answer. Sorry, what? Preserve which magnitudes?
Is it because most of the energy is in low frequency, which we don't care about? We get a lot more about high frequency signals.
The first part of that is right. I mean, it's sort of a true statement, yet a counter-explanation. So yes, most of the power is in the low frequencies. And to some extent, we don't care about the very lowest frequencies too much, but we do care about the somewhat low frequencies. And when I downsample from here to here, I'm actually only killing the very highest frequencies. I'm only killing the frequencies that are like big changes between consecutive pixels, for example. So this is how the subsampling process happens. So basically, I'm preserving almost all the power of the original signal. If I do the sum of squared values of the Fourier transform of this and this, I'll get a similar number. I'm only cropping these these super high frequencies that aren't really there anyway. Okay, so how do we subsample an image? one way that we could subsample is by throwing away every other row and column to create a half-size image. And that sort of looks okay sometimes if I do it just for if I just downsample by a factor of 2, this is the result. So here I created a smaller image. But there's one problem that we have to be aware of, which is called aliasing. So aliasing means that that after sampling a signal, you can't reconstruct the original signal correctly. So for example, with this sine wave, if I don't sample it fast enough, then if I try to reconstruct a sine wave from my samples, I'll get a different sine wave. So the same thing can happen with images, and I'll show you some examples. So you can get, for example, you see this in videos, for example. Sometimes it looks like a wheel is moving backwards. And that's actually because the frame rate is not high enough to see that it's spinning forwards. So you sample it at a too low of a rate compared to the frequency of the wheel. And so you actually interpret it as like a backwards motion. Another example is like, let me see if I actually have these. So let me just show you. So here's the illustration of the wagon wheel. So if it's moving forward, but you... so it's moving forward, and with a dot on it on one of the spokes, you can see that it's moving forward. But if I didn't have the dot there, it would actually look like a backward motion because there's a smaller motion from here to here going this way than there is going from up to the right. So if I played an animation of it without a dot, then it would look like it's spinning backwards. So this is another example. If you do graphics and you create like a ray tracer and you're not careful, you'll get some result like this. So this is ray tracing a checkerboard. And the problem is that what starts happening is you start skipping the boxes. And so then you get a whole row of red boxes in a row and a row of white boxes, and then you start getting these weird patterns because you're undersampling that more foreshortened part of the checker pattern. Here's another example. So here we start with this sort of like a checkery pattern at 256 by 256. And at first, when I start subsampling, it looks fine. But then as I go to extremes, it doesn't look like a low-resolution version of this. It has different patterns in it. So these different patterns emerge because I've oversampled without properly preparing the signal. So what do we do about this? Well, there's this theorem called the Nyquist-Shannon sampling theorem that says that when you sample a signal at discrete intervals, you have to sample it at least 2 times the max frequency. So the max frequency of the input signal. And if you do that, if you sample that 2 times the max frequency, then it's possible to reconstruct the original signal perfectly. So one thing you can do to prevent aliasing is to sample more often. But but we're trying to get a lower resolution image. So that's actually not, that's the opposite of what we're trying to do. In order to create a lower resolution image, we can't sample every pixel or more than every pixel. We have to sample less. So the solution is actually just to kill the higher frequencies, to lower Fmax. And then when we sample at a lower rate, we at least, we lose those high frequencies, but at least we don't introduce new signals through the aliasing. So we get rid of the aliasing. So the solution is to apply a smoothing filter before downsampling. So for example, we start with this image. We apply a Gaussian, and then we sample every other pixel, and then we get the small image without aliasing. So here's an example. So here, as we successively downsample, now, by the time we get to a 16 by 16 image, it's just mostly a smooth image, except for this part where it's very blocky. But we're not introducing these high intensity patterns that didn't exist in the original signal. And as you go through here, it just looks like a more blurry original image. Well, this starts to take on a new life of its own, which is usually not desirable. So here's another example with this Van Gogh. So if you keep sampling, it starts to look really blocky, like you get skin patches in the eye, and it just starts to look kind of weird. If you do the filtering, so if you filter with the Gaussian before you subsample, it gets smoother, but it still just looks like a low-resolution version of the original. It's not introducing new patterns that weren't in the original. All right, so I sort of answered this prematurely, but so what do we lose? I mean, why does it work? So it makes sense to us still because we're preserving the low frequencies. We lose the very highest frequencies, but there's not a lot of power in those frequencies anyway. So the next question is, and I think this is the last one, why do we get different distance-dependent interpretations of hybrid images? So it should be that if you're close to this image, you see more of the cat. And if you're really far away, in this case, when it's really big, you might even need to be beyond the back row, you would see my face. So let's look at some clues from human perception. So we actually don't really, even though we have cones that are receiving, basically measuring intensity and producing a signal, we have ganglia and other neurons that just immediately process that into more of like an edge-type signal. So we don't really see intensities. We see responses to kind of oriented bar and edge filters. That's kind of the basis of our perception. So the early processing filters for various orientations and scales of frequency. So here's some examples. This is like a model of some of the filters that would be applied. The perceptual cues in the mid to high frequencies dominate perception. So that's not like the very highest frequencies that you see in an image, which are like super fast changes, but the sort of moderate ones that appear around the zero frequency. When we see an image from far away, we're basically subsampling it because we'll see, many pixels will project into the same area of our visual field. And so, so from these things put together, what's the explanation? Well, actually, so first I have to also explain how we create hybrid images. So to create a hybrid image, what we do is we take a low-pass image. We have two images. One we apply a low-pass filter to, a pretty strong one, so we're just preserving the low frequencies. Another one we apply a high-pass filter to, so we're just preserving the high frequencies. And the high-pass filter is like basically 1 minus this. So it's actually, even though I'm calling it high-pass, it's also preserving a lot of the mid-frequencies. And then I get this hybrid image that's a combination of the two. Right? So why is it that we interpret the high-pass portion of the image? We see, in this case, the cat as the high-pass portion. Why, when we're close enough, is that what dominates our perception? So the answer given was because we get more samples of the details, so we see more of the high frequencies. So that's what you said, right? Yeah, that's sort of right. Yeah. So when we're close enough, basically we have access to those medium to high frequencies where we have some signal, so we can see this stuff out here. We can see this detail, and we also see this, but this detail dominates these low frequency changes. And then why does the cat disappear if we get far enough away? Or if I like go ahead and shrink this. So now you probably, it's very small, but let me put it higher too, so I don't know. All right, so now, even for me, I might have made it, let me just create a copy that's a little bit bigger too. Because even for me, I see it, but probably some of you just see a gray blob. All right, so as you get further away, then it just starts to look like a face. It's kind of like a blurry face, but a face. And you don't see the cat signal at all. So why is that? Yes?
Moving away from the subsampling, and so you're using on higher frequencies. If you like go to ice distance, I think you lose half the frequency sometimes. So that if we are doing the opposite of the Nyquist function, it's giving us we'll be losing out on the higher frequency, and that's why we see the lower ones only. Even then, since we have done a pretty steep low pass filter, even then the phase is not very clear because we have removed the higher frequencies of the phase. So that's why we see a blurry.
Yeah, that's right. So what was said is that as we move further away, we're kind of low pass filtering the signal. So we're removing the high frequencies that cause the perception of the cat. And in this case, because the cat signal was already high pass, there's actually once we remove the high frequencies, there's nothing left. So there's nothing left that we can see of the cat once we remove the high and medium frequencies. Well, we can still see these low frequencies from the face, and that's all we can see. So it's a very blurry face because this was strongly low passed, and we're basically applying our smoothing filter. But the smoothing filter that's implicitly applied when we move backwards will preserve this, and it will kill that signal. And so what we see is the low passed face. All right, so in summary, here are the things to remember. So sometimes it makes sense to think of images and filtering in the frequency domain. Like intuitively in the spatial domain, I would think that applying a box filter would give me a nice smooth image, and I wouldn't really expect to see those artifacts. But when you think about what the box filter is in the frequency domain, this 2D sync function, then you can anticipate that it's going to create some high frequency artifacts. It can be faster to filter using FFT for large images, so n log n versus n squared if you're correlating an image with itself. However, that doesn't necessarily mean I would use image Hoiem filter most of the time. And in fact, smart image libraries will usually choose for themselves whether to do the filtering with the FFT or in the spatial domain. So even though I showed examples where you do compute the FFT and dot product and do the inverse FFT, in your implementations, you generally don't want to do that. You just use Hoiem filter. I showed that for illustrative purposes. Sometimes there's confusion when somebody is new to image processing, and I show that example, and then they try to do everything by doing FFTs and inverse FFTs, and that makes your life more complicated. So images are mostly smooth, and that's a really important general thing to know about images. It's the reason why many algorithms work. And it's also the basis for compression, which is one of the things that we'll talk about next class. Also, it's important to remember to low pass before sampling. Otherwise, you can create some unexpected and undesirable results. So in the next class on Tuesday, we're going to talk about template matching, which is basic pattern matching. We'll also talk about image pyramids, which are a multi-scale representation of images, filter banks and texture, and how to do denoising and compression. So it's basically applications of filtering. All right. Thanks. Have a good weekend.